السلام عليكم. الفيديو فيه جزئية متعلقة بقياس سرعة الضوء في اتجاه واحد. بيقول دايما بتحصل مشكلة في الساعات اللي ممكن ترصد اللحظة الزمنية، وبيقول عشان ممكن نحل المشكلة دي نعمل ايه. هنحط ساعتين ذريتين جنب بعض ونزامنهم في وقت واحد بساعة ذرية وبعدين نحركهم في اتجاهين مختلفين للشرق وللغرب بنفس المسافة. بيقول المشكلة إن ممكن يحصل تباطؤ للزمن أو تمدد للزمن بمقدار مختلف نتيجة اختلاف الاتجاه. طيب هو اختلاف الاتجاه هنا هينشأ من إيه؟ ما هينشأ عن دوران الأرض، وأنا أقدر أعرف السرعة الكلية للمرجعية وأطرح السرعة دي وأزود السرعة دي. يعني لو كانت سرعة حركة الساعة للشرق وللغرب ولتكن مثلا عين واحد وأنا عندي سرعة دوران الأرض، في حالة الساعة الشرقية هيكون التغير بمقدار سرعة دوران الأرض زائد عين واحد، بينما في الحالة التانية تبقى سرعة دوران الأرض ناقص عين اتنين. وبكده نبقى حلينا المشكلة إذا افترضنا إن في اختلاف في الجهة هيؤثر على تباطؤ الزمن. تباطؤ الزمن في الحالة التانية لو مش هيتأثر على الجهة هيكون بمقدار حركة الساعة بس زائد سرعة دوران الأرض، فنقدر نحسب تباطؤ الزمن. طبعا سرعة دوران الأرض في الحالتين واحد، هيبقى الفرق بس في سرعة الساعة. سرعة الساعة واحدة يبقى تباطؤ الزمن واحد. لو في اختلاف هنعرفه ازاي؟ أحسن حاجة إن احنا نعيد التجربة أكثر من مرة عشان نتفادى هذا الأثر. بس اترككم مع الفيديو وانتظر تعليقاتكم.
But again, this only works if the speed of light in each direction is the same. If the speed of light depends on direction, then so does time dilation. If the speed of light depends on direction, then so does time dilation. But again, this only works if the speed of light in each direction is the same. If the speed of light depends on direction, then so does time dilation. If the speed of light depends on direction, then so does time dilation. What if you center a synchronizing device between your two clocks and send out simultaneous pulses? Well, if the speed of light is the same in both directions, this perfectly synchronizes your clocks. But if the speed of light is different in each direction, one of the clocks will be ahead of the other, and it will be ahead by just the right amount, so that when you measure the speed of light, you'll find the value to be c, even though that was not the speed the light was traveling. This is the same reason GPS synchronized clocks won't work. The whole GPS system is based on the assumption that the speed of light is the same in all directions. If the speed of light is different in different directions, the light pulses from satellites will travel at different speeds, so the clocks won't be properly synced. By that I mean they will always measure c for the one-way speed of light, whether it is or isn't. How about starting with synchronized clocks in the middle and moving them apart with equal and opposite speeds? That way the time dilation for each clock will be the same and they'll still be synchronized when they reach the endpoints. But again, this only works if the speed of light in each direction is the same. If the speed of light depends on direction, then so does time dilation. If the speed of light depends on direction, then so does time dilation. But again, this only works if the speed of light in each direction is the same. If the speed of light depends on direction, then so does time dilation. If the speed of light depends on direction, then so does time dilation. You might think you could move the clocks really slowly so that time dilation is negligible. But if the speed of light is different in different directions, you can't just use the standard formula to calculate what that time dilation would be. I mean, it could be a lot worse than you think. So the reality is we're stuck. We need synchronized clocks to measure the one-way speed of light, but we need to know the one-way speed of light in order to synchronize our clocks. Now this might sound like just an academic concern, so I want to go through an example to illustrate just how differently the universe works if the speed of light is not the same in all directions. Let's say on Mars, Mark is trying to synchronize his clock with the Earth. At noon, Mission Control sends out a message that says, "This signal was sent at exactly 12 o'clock." When Mark receives this message, he uses the Einstein synchronization convention to set his clock. He knows the round-trip time delay is 20 minutes, so he assumes the signal must have taken 10 minutes to reach him. He programs his clock to 12:10 p.m. and sends a return message. This reply sent at 12:10. The message is received on Earth at 12:20 p.m., so both parties know the synchronization was successful. When the clock reads 12:20 on Earth, it simultaneously reads 12:20 on Mars. But now consider what happens if the speed of light is not the same in both directions. Let's say it is c/2 from Earth to Mars, and then instantaneous from Mars back to Earth. No one knows this, of course, so they continue to use the Einstein convention. The message is sent from Earth, but now it takes a full 20 minutes to reach Mars. But Mark doesn't know this, and as before, he assumes the signal took 10 minutes to reach him, so he sets his clock to 12:10 p.m., even though on Earth it is now 12:20. Mark then sends this reply sent at 12:10 p.m., which is instantaneously received on Earth at 12:20 Earth time. The experience for the two communicators is the same. The same messages were received with the same local time delays, but their clocks are out of sync by 10 minutes. What they think is the same moment for the other observer actually isn't, and there is no way they can ever recognize or correct this error. Imagine if someone on Earth immediately responded, "How long did this message take to reach you? It's now 12:20. Well, the message would take 20 minutes to reach Mars, but due to the clocks being out of sync, it would arrive at 12:30 Mars time, so Mark would reply 10 minutes, a message that would instantaneously reach the Earth at 12:40 Earth time. The space-time diagram shows how there is flexibility in what you consider to be the same moment at two different locations, and in how you define the one-way speed of light. Einstein chose the convention where the one-way speed of light is always the same, but from an experimental perspective, any other convention is just as valid, up to and including one where the speed of light is c/2 one way and instantaneous the other way. And in that case, it's interesting to think about what each observer is seeing when they look at the other. Mark would be seeing the Earth as it was 20 minutes ago, but Earth is seeing Mars in real time, exactly as it is right now. And this effect wouldn't stop at Mars. Look beyond it and you could see stars hundreds of light years away. Not as they looked centuries ago, but exactly as they are right this instant. One of the things is, you only know about that light when it reaches you. And you don't know anything about what journey it took to get to you. You just see it and it's there, so like it's instantaneous. So an instantaneous interpretation of that light is just as good as one where it takes C to reach us.
This is breaking my brain. Yeah, I mean, it's kind of unknowable, isn't it?
It is unknowable. That's the whole point of the video. Is to say, we've all agreed, and this is based on something Einstein wrote in 1905, we've all agreed to just say, it's C in every direction. But the truth is the physics works the same, whether it's c or the c/2 and instantaneous, or anything in between. As long as the round trip works out to be c, none of physics breaks. And that's the crazy thing.
So if we can never measure the one-way speed of light, and if it makes no difference to any of the laws of physics, then what's the point in even talking about it? Well, that is certainly one valid perspective in a debate that has been ongoing since 1905. Some physicists appeal to Occam's razor. Isn't it just simpler if light travels at the same speed in all directions? Most working physicists just accept the convention and move on with their lives. But I think it's important to point out that it is just a convention, not an empirically verified fact. Personally, I find it fascinating that this is something about the universe that is hidden from us. Sure, the round-trip speed of light is c, but does the one-way speed even have a well-defined value? And if it doesn't, what does that mean for the concept of simultaneity? When is right now on Mars? Does it even make sense to talk about things happening at the same time if they're separated by distance? Maybe this is an odd quirk of the universe and there's no good reason for it. Or maybe when physics takes the next paradigmatic leap, our inability to measure the one-way speed of light will be the obvious clue to the way general relativity, quantum mechanics, space and time are all connected. And we'll wonder why we didn't see it before.